Greetings, a cyclic group is a group, and I'm not going to go deep into this because our goal here is to prove if a subgroup of a cyclic group is cyclic. So let's suppose we already know what a cyclic group, but to just roughly repeat what it means. And this is not like going into details. Cyclic group basically is a group where you can just take one element of it and put it into operation with only itself, so identically the same element, to some different powers, and generate all the elements of that group. And it ends up being a group, all these elements together as element set, satisfy the group axioms and so on. And now let's prove that a subgroup of a cyclic group is also cyclic. So I suppose we have a subgroup H of G. And if the subgroup is equal to the original group itself, that's a trivial case. Also, if it's only equal to the identity element, it's trivial. Both cases will be automatically cyclic because it will just either be equal to the group. So if this group is supposed to be cyclic, then of course something equal to it, because the subgroup could be equal to the original group, a potential subgroup. I mean, the most simple idea is of course cyclic because it's just the same group. If it's only the identity element, then just putting it into operation with itself, the order of that group doesn't increase. We cannot generate. We'll just keep generating the same. We stay at the identity element by the property of the identity element. So that's the two things we kind of want to avoid. Now we just want to concentrate on proper proper subsets in terms of what is the element set of that subgroup. So it's relative to the original groups, or the element set will be a proper subset, something in between, not only the identity but also not the whole group. And if we suppose that, first thing, let's suppose that we choose m in natural numbers, and by natural numbers I mean 1 and higher positive integers, not 0. Choose m in natural numbers such that g to the m equals, and by the way, lowest. That's an important part here. So choose lowest, that's so crucial, okay, not to forget this part, the lowest part. So choose lowest m inside positive natural numbers, such that, or natural numbers we can define a 1 and higher, so self-explanatory in that sense. Someone defines them to also include 0, but we don't want that variant. We want the variant where natural numbers are defined as 1, 2 and higher, 3 and higher. Anyway, g to the m is the lowest possible power of g, by the way, the same generator as capital G hat, such that, so we say some power of g is the lowest potential power of g, of the original generator of g, such that it's contained also in the subgroup H. Alright? I mean, if H was the whole subgroup G, then already G to the 0, G to the 1, if you're talking about positive integer power, G to the 1 already would definitely be in H also, if H was equal to G, but we said it's not necessarily equal to G. So, yeah, let's choose this to be the lowest potential power such that G to M is already in H. Right? Could be G to the first is not yet in H, but it's in G of course. But G to the second or third, some higher integer, finally it's lowest integer, positive integer possible, such that G to them is actually inside H. And then we want to see that the subgroup H is generable by one element, namely this one. So this is the whole point of this idea, of this proof. We want to see that H is a cyclic group, definition of a cyclic group, generatable by only one element. And we pick this G to the m, the lowest possible power of the original generator G of G, such that it's already inside the subgroup H. And we want to see, is H a cyclic group in a way that is generable by this G to the m? Well, a number, if it's generable, it means that just like every G inside G, for every G inside G, it applied that or let's say for every, because this would be the same letter, so for every A inside G is applied, A is a integer power of the generator G. So if we say H is cyclic and say this G to the m is the generator of H, that means that every, let's do analogy, let's say B inside H, any element inside H is generatable by this. Question mark, alright? And now the idea is, well, there's different ways we can think about it, alright? Because let's say that the things, let's say that we will call the elements of H, I will say H is the set, this element set of H will be G to the N, as N is in integers. And so that means we now want to see if those N's are multiples of the K, of the M. We want to see, are they direct multiples, integer multiples of the M? Why? Because we want to see that every element of H is a power of G to the M. And that means by integer, exponent properties, it's G to the M to something more. So that G to the M to something more will be equal to the G to the N. But we want to see, is this compatible with the division algorithm, the Euclidean division algorithm, which basically N is a multiple of M, integer multiple of M, only if R is 0. So you want to see if that's the case. And now we proceed. So if we say that H, any element is G to the N, well, before we said it's any power of G to the M to some integer power, well, we say that G to the N must be G to the M to some integer power. But that could only work if R is 0, but let's now prove that R must be 0. So that means that G to the N will equal to the G to the M Q plus R. And we're now going to use, we're basically using exponent properties in order to prove something in graph theory. So that's interesting. We're using basic algebra exponent properties because by exponents we really can talk about cyclic groups, order of elements, and so on. When abstractizing about elements in general, when we can call the when we talk about powers of elements, especially if it's the same element with itself, the generating element, and so on. Alright, so let's rewrite this a bit and see G to the M Q times G to the R. Alright, well, we suppose that G to the, well, let's say this is H, alright? So H consists of basically H is equal to any possible G to the N. Well, so let's now manipulate this a bit. We suppose H is, lowercase h is a member of this subgroup H definitely. And let's say apply the left operation to invert this thing here. So let's just do it on the left like this. We found out that now G to the minus MQ times H, I just reapply this to the left side to get rid of this and just isolate the G to the R, and I put it into interaction with this H on the left side. This should be equal. We know this is inside H, the group H, and this also should be, because we suppose G to the M is, well, this thing is also inside H, in short. And why? The reason is G to the M is in H. G to the M, now we can use exponent properties to write it as G to the M to the minus 1 to the Q. Or we multiply the exponents in one like this, just exponent properties. So G to the M is in H, then we could put the minus as a minus 1 above it. G to the M to the minus 1 is just an inverse to it. Group has to have inverses for all elements, so that's also true. And to the Q, well, Q is some integer in this division algorithm. In the Euclidean division algorithm, Q is an integer. And there's one very important property. 0 must go, R must go between 0, can be equal to 0 or higher than 0 and smaller than the M when we write it out like this. But important fact to go back to is, we had said, we suppose M is the lowest integer, that this works. And if we said now, this is in H, two elements put into binary operation with each other who are both in H, the result must be in H. That means that G to the R must be in H. Alright? But we have now an interaction of two facts. We introduced the Euclidean algorithm, which has this one big property, the way we write an integer as basically factor times Q plus another integer R, that if N is directly integer multiple of M, because Q is logically in an integer also, this is all integers here, by the way, this is all integers here, then R will be 0. So if it's n is a direct integer multiple, then r becomes 0. If there's a remainder, then it's not a direct integer multiple, right? And it interacts with this side big fact, because that's how the algorithm is supposed to work. R should be smaller than m, so we can fit as many increase the m as much as possible, and then just have r to be the remainder. And r can be smaller than m, but it could also be 0 if there's no remainder. And at the same time, we chose that the smallest possible m, such that g to the m is in h, is m. The smallest possible exponent, g to something, such that g to that something is still in h, is that m. So g to the m is the smallest possible power of the generator g, such that it's in h. So that means g to the r must be, this was the smallest possible positive integer power. So r can be either bigger than m, or it must be 0. It cannot be between 0 and m. And it cannot be bigger than m by this information, and it has to be, and it also cannot have the place that m already holds by this. So for that reason, it implies r equals to 0. So by this we prove that this is cancelled out. By this we prove n equals nq. And we said thereby that if we say any element h, we call it g to the n, that n must be a direct integer multiple of m by the factor q. And that means that basically from all this information, any h inside h is equal to g to the m to the q, right? Well, in other words, g to the qm by exponent properties. Alright? That means that any element in h is generated by g to the m by taking it to any integer powers. Q can be then any integer. So this was an interesting proof. I mean, we had some group G and we took some subgroup H, and we set m to be the smallest positive integer power for the generator G from the original group in order for G to the m to be in H. Then we also introduced the Euclidean algorithm. These numbers are integers and there's this additional property to them. A Euclidean algorithm aids us or helps us in being able to break down integer into a into some multiplication of integers plus a remainder. There's a remainder if you want to divide it by m, and we say how many times the m fits there, and then remainder. But if there's no remainder, r must be 0. Well, we found out that r is indeed 0 by the property that m is the lowest possible exponent, such that g to the m is in h if it's a positive integer. And also we found that r must be between m and 0. So if m must be the smallest positive integer, then r, the only option for our left is that it's equal to 0. So that's that for this proof.